ॐ सहनाववतु सहनौ भुनक्तु सह वीर्यं करवावहै तेजस्विनावधीतमस्तु मा विद्विषावहै ॐ शान्ति शान्ति शान्तिः।
In the last class, we saw the Rayleigh-Ritz procedure. As I told you, Rayleigh-Ritz procedure is a forerunner to finite element analysis, and I hope you understand. If there is any question, I can answer that. Yeah, one of the questions that is asked is, how is that A0 became 0, right? Because if you remember, we started with u is equal to A0 plus A1x plus A2x squared and so on. Why did you make A0 is equal to 0? See, in that procedure, it should be such that the displacement boundary condition that has been given, which is an essential boundary condition, should be satisfied by that particular polynomial. So in other words, at x is equal to 0, u has to become 0, which means that A0 becomes 0, right? Okay. So now we move over to the finite element analysis. What is the difference between finite element analysis and whatever we did? The difference is very simple. In the Rayleigh-Ritz procedure, we considered the complete body. Okay, remember what we had put down? We had just put down this, and then we said that we will consider it as a complete body. So in Rayleigh-Ritz procedure, we had the body to be taken as it is, as if it is one element, right? But what we are going to do in finite element analysis is to split this body into number of elements. So in other words, we will proceed as if we are going to apply this procedure to more number of elements. Is it clear? So that's what we are going to do in this case. Okay, before we proceed, let us look at how to write down the potential energy for a body. Okay, the potential energy term is written down completely like this. You will see lot of terms here. Okay, have a look at this whole thing together, and I'll explain each of them very carefully, right? Each of them very carefully. Now look at those terms. You have the first term. What is the first term? First term, do you remember what the first term is? What is the first term? Strain energy, okay, term. Please note, you are used to writing half sigma epsilon. Now what I have written, essentially for a multi-axial case, okay, I have written it in terms of a matrix notation, epsilon transpose d epsilon. Okay, our old E now takes the value or takes the shape of d. Is it clear? Okay, so the first term indicates in this particular expression the popular strain energy term, we all know it. Look at the second term. You have now a new epsilon 0, okay, a new term called epsilon 0. Now in this case, what we have essentially done is to consider a body with an initial strain and an initial stress. Let us see what happens to a body when there is an initial strain and an initial stress. So epsilon 0 is an initial strain, and sigma 0, which comes in the next term, is the initial stress. Is that clear? Or in other words, what does it mean? It means that the body has some strain, okay, due to say assembly or fitting or whatever it is, some initial strain. It can be due to say thermal stresses. This kind of thing can be present. So sigma 0 and epsilon 0 indicate the state of the body when you start loading them, right, or in other words they are something external, okay, due to something external that has happened to the body, right. Okay. Now look at this term now, sigma transpose epsilon 0. Look at the second term, okay, sigma transpose epsilon 0, and look at this third term, okay, epsilon 0 transpose sigma, or these two terms, or sorry, I think it should be sigma 0 transpose or epsilon transpose sigma 0, okay, sorry, yeah, because epsilon 0 and sigma 0, I just repeated that. So these two, look at these two terms, okay. What does it mean? It means that when I start loading the body, because of these pre-existence of the strains and the stress, okay, they start doing work, okay, and hence these two there are minus signs. So these two terms come from initial strain and the initial stress. Is that clear? What is the next term? What's the next term? Due to body forces, okay. Please note these two are different from body forces, right. In the previous problem itself you would have noticed that what we were specifying as, what did we specify, Cx, okay, the C is force per length squared and so on, was nothing but a sort of a body force that we were specifying. We were specifying throughout the volume or throughout the length of the body, right. Okay. Now what is this term here? What is this term here? That term is due to surface forces, right. It is the work done due to the surface forces, right. So you would see all those minuses there. What does it mean? It means that the potential for these external loads to do work is now getting lost. Is it clear? And look at that last term. Last term I have just added it now, specifically maybe you wouldn't have seen it. I have just added it here because we are going to also meet concentrated loads, okay, in a finite element situation. So there are going to be nodes and you may put a concentrated load at a node, okay. That is why I have put that, the last term I have added it. The last term depicts the work done by concentrated load. So this completes the definition of potential energy for a body when it has an initial strain, an initial stress, surface forces, body forces, concentrated loads, and apart from an elastic type of constitutive equation. What is my goal? My goal is to now develop or reduce this into an algebraic set of equations. How am I going to do it? Let us see how we are going to do it. Now please note that in my previous derivation on Rayleigh-Ritz procedure, what is that I did? I had put down a degree of freedom as A1 and A2 and so on. Now what I am going to do right away is to swap this A1 and A2 with U1 and U2, or Ui and Uj to be more general, right. Is that clear? How am I going to do that? Now the first thing that I am going to do is to take an element, say Ij, okay. Let us take that element Ij. Let us say that the length of this element is equal to L, okay. Now I am going to put a local coordinate system to it. Let me put a local coordinate system such that it is depicted by S. What does it mean? S is equal to 0 at I and S is equal to L at J. Is that clear? Okay. Let me now write down an expression for U. How do I write down an expression for U? U is equal to A1 plus say A to S. Now, what we are going to do is to replace A1 and A2 in terms of Ui and Uj. Ui and Uj within quotes, known values, or in other words, what we are going to solve. Okay, Ui and Uj are the ones which we are going to solve. You already know a procedure for solving them and so on, right? So I am going to replace A1 and A2 by means of U1 and U2. Okay, so till now the procedure is the same. Please note here that I am not going to put A1 is equal to 0 because there is no boundary condition here. Okay, we are treating a separate element. We are going to put the boundary condition later only. Is that clear? So I am going to put first U is equal to A1 plus A2. Now can you now substitute Ui and Uj and give me an expression for U? I will give you 1 minute, so let us see whether you do it fast. Let us see how you are going to express U in terms of Ui and Uj. What's it that you are going to do? You are going to put S is equal to 0, U is equal to Ui, S is equal to L, right? S is equal to L, what happens? U is equal to Uj. So you can express this as one minus S by L into Ui plus S by L into Uj. Right? Is that clear? Okay. Let me write that as N Ui Uj. Right? What is N? N is nothing but 1 minus S by L, S by L. Right? So if you want, this N is what is called as the shape function. Note this carefully, that N is called as the shape function. People call this also as interpolation function, okay, basis function and so on. Okay, essentially they are either, they are called by one of these names, but essentially they are the most important input, okay, for finite element analysis. Is it clear? Have a look at that and see whether you can straight away get one or two properties from it, 1 minus S by L and S by L. Straight away you can see one or two things. What are they? They are nothing but an interpolation function because it interpolates U, okay, by or getting the values of Ui and Uj. So they are, that's why they are called as interpolation functions. Is that clear? And one more thing you can straight away notice that. What is it? That sigma of n is equal to 1. Okay. If I call this as say n1 and n2, okay, then sigma of n, that is n1 plus n2 is equal to 1. And what is the other thing that you can see from this? What happens when S is equal to 0? N is equal to n1, n2 is equal to 0, right? So 1 minus S by L, and S by L is such that n1 becomes, n1 becomes 1 at S is equal to 0, and n2 becomes sorry, n1 is equal to 1 at s equal to 0, and n2 becomes 0 at s is equal to 0, and vice versa. When s is equal to L, the first fellow goes off and the second fellow remains. Is it clear? Any questions on this? Okay. Now let me write down u as n d. Now I can write down the same procedure by means of a much more complicated matrix notations and so on. I'm just, because I'm just introducing this topic, I have written down like that. Okay. Now this kind of from A, moving from A basis to this n basis, okay, can be done for much more complex case as well. Is that clear? Okay. Now have a look at that first expression, u is equal to a1 plus a2s. U is equal to a1 plus a2s. Suppose yesterday, if you remember, that we had put a2s plus say a3s squared. Suppose I put a1 plus a2s plus a3s squared, what am I going to do now? Yes, what, pardon? Third node. In other words, I can't swap now with two nodes, so I have to put one more node. Okay. Now I will have u is equal to ui, uj and uk, or u1, u2 and u3, however you want to call it, right. So you can now have 3 nodes and 3 coefficients which can be swapped. So what does it mean? It means that as you increase the degrees of the polynomial, I will also have to increase the number of nodes which go to define the element. Is it clear? And these elements, where I have used higher order or higher order polynomials, are called as higher order elements. Now if I now have to do this, like replace a1, a2 and a3 by means of u1, u2 and u3, okay, if I keep on doing this, this procedure becomes a bit difficult, because I have to sort out or solve these equations like this. So we are going to work out a better procedure to do it. We are going to look at some well known interpolation functions. Later in the day, or maybe in the next class, we are going to look at what are called as Lagrange interpolation functions. Is that clear? Okay. Now probably you would have already heard about Lagrange interpolation functions and Hermitian interpolation functions and so on. We will look at that Lagrange's interpolation in the later in the class. Okay. Right now let us say that we can write down u, okay, in terms of n and d. Okay. This is one dimensional problem, but if I happen to have a 2D problem with, say, for example, an element like this, then how many degrees of freedom I am going to have? U and v. Okay. In which case I have to write down u as like that, which depicts u and v, right. And what is going to happen now to d? How many entries did I have here? I had only 2 entries. But when I now shift to a 2-dimensional case, how many d's I will have? Is it 4? Look at that, 1, 2, 3, 4, and each of these nodes will have 2, correct. So I will have 8 entries. So n will correspondingly change, right. Okay. So in general I can write down u is equal to n d. Is it clear? Any questions? In general I can, what is this n? Don't worry about it now. What is this n for this 2D case? Let's not worry about it. I can get you that very easily, it's not difficult. But right now accept that u can be written down in terms of nd, or in other words accept that shape functions can be determined for different types of elements. Okay, when things become very complicated, we will move away from this very simple thing. We are going to move away. We are going to talk about what are called as isoparametric elements and so on. Let's not worry about it right now. But right now we will accept that u is equal to nd can be written. Clear? Okay. Now what is my next step? Just think for a minute and tell me what is my next step. What do you think I should do as the next step? Now, in order to do that, have a look at this expression here. Have a look at this big expression here. Okay, and tell me what is it that I should get from u is equal to nd. Epsilon, right, beautiful. So you are very logically looking at things. Okay, epsilon. Fantastic, that's what I wanted. So epsilon can be written in terms of my displacements. Okay, so I'm going to get strain displacement relationship. Remember, how did we write it? U, in terms of u, previously we had written it epsilon 1 1, epsilon 2 2, epsilon 1 2 and so on, or gamma 1 2, we had all those things set up already, right? Okay, just a second, we will write that down. Let's follow a notation and say that u, by the way, you have to tell me which is that you are going to differentiate. Nd is there. Okay, because you have to apply differentiation. Oh yeah, that's what I was waiting for. Is that d? What is d? What does d contain? Yeah, they are constants. They are in terms of degrees of freedom. So I am going to say, for example, I am going to differentiate this element with respect to s, which is the local coordinate system, which is something like x, right? So epsilon, I have to differentiate it with respect to x. So it will be in terms of n. Okay, so let me call this as, so epsilon is equal to some dou term n d. Okay, what is this dou matrix? Can you think about it? What is this epsilon? I mean, sorry, I think I have to put like that. For 2D, for example, epsilon is epsilon 1 1, epsilon 2 2, gamma 1 2 and so on. Okay, you can keep expanding epsilon for 3D as well, right? So what is this matrix, dou matrix? No, that's beautiful. So that is it. So that matrix is dou by dou x1, okay, 0 0 and so on. Can you fill it up? So next line will be 0 dou by dou x2, then dou by dou x2 and dou by dou x1, right? That is now multiplied, or this operator, you can say that dou is an operator. Now it operates on n, right? It operates on n, right? Is that clear? Okay. Now I am going to ask you one more question. Just think about it. Even though you don't worry about what is inside n, you have to tell me what is the size of dou n and d. Okay, you have to tell me what is the size of dou n and d for a 2D case. Let's say 2D case. Look at this. You have to tell me what is the sizes of them. What is the size of dou n and d? What do you think? Dou is it 2 by 2, 2 by 2, or what? 3 by 2, and then n 2 by, come on, 2 by 3, 2 by 4, 2 by 8. I get all sorts of answers. See, it's very simple. It's very simple. Look at D. D is what? What is D? 8 by 1. Come on, that's it. 8 by 1. So what is N? 2 by 8. That's it. 2 by 8. So what is that ultimately you will get? How do you get it? How do you see it? 3 by 1. So that is what is epsilon. Yeah, just have a look at that. You shouldn't get confused. See, this is very, very important to understand. So what the sizes of this matrix are. Because when we assemble, when we put them together, it is these sizes which are going to confuse you. That's why I am right now emphasizing what should be the sizes of these matrices. Right? Okay. Having understood that, let me call dou n as a B matrix. Let me call this dou n as a B matrix. So that epsilon can be written as B into D. This is the most important part of the whole finite element, so I want you to concentrate. If there's any doubts, just ask me. Yeah. So I can write epsilon is equal to B D. Okay? Clear? Now what is my next logical step, my friend? Yeah. He said, what is my next logical step? What is that I should get? What is the what's the next logical step? What is that I should look for? Stress strain matrix. Beautiful. Okay? We have already derived that. That's why I did all those things initially. We know everything now. Okay? I already know what this D matrix is. Right? So I can write down that I have already written down. Sigma is equal to, I am not going to repeat that, sigma is equal to D epsilon. In our earlier classes, we have spent a lot of time looking at D. So I will just write down sigma is equal to D epsilon. So I can say that sigma is equal to D B, okay, into D and so on. Any questions? Right. Now, having got all these things, what am I going to do? I am going to substitute them into this expression. Okay, I am going to substitute all of them into this expression. I would like you to do it because it is straightforward and gives you an exercise. So I will give you 1 minute to write this down. Just attempt it. What is that you should know? That AB transpose is equal to, what is AB transpose? B transpose A transpose. That's all you should know. Okay? Now write it down. I will give you a minute. Have a look at this expression, and then write it down. And after a minute, let me hear what you have done. This will give you a good exercises to remember each of these things. Just put that down. Let us see, have a look at this. Okay? Look at each of the terms and replace. All the while, think about the size, for example, for a 2D problem. By the way, notice that phi p is a scalar quantity. Okay, phi p is a scalar quantity. Don't look at what I am going to write now, because I would like you to write it. Okay, I am going to write the final result, but have a look at this and you keep writing it so that you will get a feel of what's happening. So, all of you have written the first term, is that okay? Minus, so epsilon transpose, what is epsilon, sigma transpose epsilon 0, okay. What is sigma transpose? Epsilon transpose D transpose. So, what is epsilon? I want you to substitute till the end. Yeah, D transpose. See, all of them are matrices. I'm not putting everything as a matrix. No, you know they are matrices. Okay. So, D transpose B transpose D, capital D transpose is it D transpose? B transpose D transpose here. So, what is the next term? Minus, where is that? Yeah. Still you are writing? D transpose B transpose sigma naught right, and then next term minus V D transpose N transpose F dV, okay. That's the next term, that is for what? For body forces, okay. Then for surface forces, D transpose N transpose phi, sorry, ds. Yeah, any questions? Okay. Now, lastly, I have that D transpose P, okay, minus D transpose P. Now, just to make it simplified, I am not going to enter, or I am not going to carry on those two terms, that epsilon 0 and sigma 0 terms. It is very easy to include them because I have to write down big expressions, okay. You can very easily take it down. So, I am going to just remove that for the time being. If you want, you can always add it, okay, to make it much simpler, right. Okay. Now, I am going to define a stiffness matrix as integral B transpose d B dV. Okay. Let me define K, stiffness matrix of an element, to be integral B transpose dB. Is that clear? And this is for a general body, okay, but in the sense that it is for an element as well, and or for the whole body. You can look at it either way. But since I have written down this last term here, it is for the whole body which has been already discretized. Is that clear? Okay. So, now I am going to do one more thing. The small d's here are actually, there is a small problem. The small d's here are for the element degree of freedom, right. I am going to expand them Actually that is, so that is why I am very careful in writing the last term, they do not go with this. So there is always a trouble as to understand that. Okay. So what I am going to do is to expand that small d to the whole of the matrix, or in other words, if I have an element which runs say from 1 and 2 nodes, I am going to say I will write as if it is 1, 2 and other things being 0 up to say 20 elements, if the problem has 20 elements. Okay, I am going to expand them. Why is that I am going to expand? If I expand like that, it is easy to add them, okay, right now, but computer implementations are not like that, they are quite different. Okay. So let us not worry about that at this moment, and so let us see how we can write down this particular case, right. Or in other words, what is that we are doing? We are expanding, or in other words, we are substituting for small d by capital D, substituting small d by capital D. Capital D indicates a vector which covers all the nodes in the body, which covers all the nodes in the body. Is that clear? Okay. Now write down the expression now. Let us see how you can write down that expression. So define Ke as integral V B transpose dB dV. Okay. And when I expand it to d, the total phi p of the whole system can be written in terms of, okay, in terms of capital D. So I can write that d transpose d, okay, for the as a contribution of this element strain energy, okay, of course half is there, half as a contribution of strain energy of one element to the total system. Is that clear? No? Okay. Let me repeat that. Have a look at this again. What is this small d's? What is the small d's? They are for element. Okay. So in other words, what it means is each element now contributes for phi p. In strict terms, this phi p what I have written is valid only for an element. Okay. But I have just added this term, this is not right to do it to the last term, please note this is not the right way of doing it, but I just wanted to remind you that there is the last term there, there is one more contribution from concentrated loads. Okay. So I would say that I have just added it more symbolically there. For the time being you forget it, okay, if there is a confusion forget it for the time being. Okay, we will add it in the next step. Okay, I said that I have added it very symbolically. So each of the element contributes to strain energy and each of the element contributes to potential lost. Okay. So what is that I should do if I want to find out the complete phi p of the system? I have to add because each of the elements, I have already divided the whole body into number of elements. So I have to add the contribution of each of the elements as far as the strain energy is concerned, as far as the potential lost due to internal loads, or in other words due to body loads or body forces and so on, right. In order to do that, in order to add, I can't add straight away because my d's, small d's there sitting there, they are different. The first element may have 1 and 2 node, the second element may have 2 and 3 nodes, third elements 3 and 4 nodes and so on. So how do I now add? Tell me a procedure how to add it. The best thing is to expand that small d to the whole of capital D, right, so that others will be 0. Okay, I will just give you a minute to understand this. Okay. What I am going to do is to put down my old problem, you know my old problem, and write it down in terms of the entire degree of freedom. Okay. What is that old problem? Say for example, let me say that I have 4 nodes. Okay, I have 4 nodes. 1, 2, 3 and 4. Okay. I have an element 1 which connects 1 and 2, element 2 which connects 2 and 3, and element 3 which connects 3 and 4. Okay. I have these 3 guys sitting there. Now element 1 has k1, say for example k1 minus k1 minus k1 and k1, and the corresponding displacements are u1 and u2. Now I am saying u1 u2, make it u1 u2 u3 u4, make it u1 u2. So how will the k change now? That is what I want to ask you. Just a minute, write it down, try it. How does it? I mean, it's very simple. I mean, very obvious question, but I know that it is not very easy to follow. So you please try it and write it down. I will write it down in a minute, what exactly I mean by that. Have a look at that, and then have a look at this, and then write it down in terms of, say, let us say that this is the element 1. It is very straightforward question. So what I am saying is that the K matrix will have now 1, 2, 3, 4, u1, u2, u3 and u4. So what will happen to the K matrix? I am expanding it. What will happen to the K matrix? Zeros, that is it. You know, that is what I have been looking for. It took you quite a while to find out. Okay, so k1 minus k1 0 0 minus k1 0 0 and so on. What is the advantage now? The advantage is that if I write the second element also in the same sense, how do I write it? 0 0 0 0, first 0 0 0 0, then second row becomes 0 k2 minus k2 0 and so on. Then these are straight away they can be added. They are matrix of the same size, and not only that, these u's that are sitting there, they are the same u's. So u can be taken out and I can add them. Is that clear? No? Still not clear? What I have done is to facilitate adding of k. What I have done is to facilitate the adding of k, or else I can't add k straight away, because this k1 corresponds to this 1 and 2, k1s or k's corresponds to 1 and 2, the k2 corresponds to 2 and 3. So I can't add k1 and k2 straight away. So unless and until I expand it like this. Right? Though it is not an efficient way of doing things in a computer, let me make it very clear, this is not the way commercial code is written. Right now as students, it is easy to understand what is happening. There are different ways of doing it. We are not looking at computer implementation straight away. Okay, we are not looking at computer implementation, we are only looking at how to do things now, how things are done. Okay, hence this is a nice way of looking at things, right? Okay. Now get back to this. Get back to this question. Now I have already defined ke, okay, and u, this is not ke of course, that is the u, the contribution of u of an element. Okay. Now complete this thing. I am making you write because it is easier to follow when you start thinking and writing down. Right? I will give you 1 minute, just write down or convert it and write down. I want something like this. I want ultimately k into d is equal to r. This is the expression I want. Okay, k d is equal to r. How are you going to write it down? That is the question. Just try it for a minute. I will give you all the clues that are necessary. One is ke can be ke can be summed up, or k can be sum of ke's. Okay, capital K, let us call that as capital K. Capital K is equal to sum of ke's. Then you look at also RE's. what is RE? What is RE? RE is the other terms. Say for example, D transpose, take it out. So RE is equal to minus N transpose F dV and minus N transpose phi ds. Is that clear? Now, so in other words, what is that you are going to get ultimately? Yeah, write it down. Okay, we have another 2 minutes, just write it down. I will do that, I will write it down, but just see how you are going to write down. So I can write it down as half capital D transpose KD minus D transpose RE. What is the next term I will have, or R rather, minus D transpose P will be my phi P. Okay, that is the total phi P is equal to half D transpose KD. This K is the sum of sigma of K's, okay, minus D transpose R. This R is sigma of REs, right, minus D transpose P, that will be phi P. K is equal to sigma of Ke. This is a matrix addition because I have already expanded K in terms of complete D, and R is equal to sigma of REs, right? Is that clear? Okay. What is my, is that clear? And the last term now I have brought in because my phi P now should include the contribution due to concentrated loads. Please remember what is RE? RE is nothing but N transpose F dV N transpose phi ds, that is RE. So in other words, this will come out and that will come out. Right? So what is my next step? What's my next step? Yes, that's it. So d phi P by d should be equal to 0 independently. So in other words, dou phi P by dou d I 2 or I where I is equal to 1, 2 and so on should be equal to 0. So what is it that I am going to get? A matrix, correct, but what is that? Half D transpose KD, when you differentiate it with respect to D, becomes KD. You can work it out by hand, okay, KD. So the first term now, after I differentiate this, becomes KD, okay, minus R minus P, and that is equal to 0. So KD is equal to R plus P. That is my final expression. KD is equal to R plus P. K comes from small ke, okay, which is, what is it? Integral B transpose d B dV. Yeah, I think only small thing is that, see, usually I think there is a small error here, that sigma 0 is usually replaced by means of, I think that is the only mistake you did when you expanded, by d into epsilon 0. That is how you expand. So I think there was a, you said d transpose, that is what I was surprised. Actually you write sigma 0 as d epsilon 0. Did you get it correctly? Okay, d epsilon 0, and this is equal to sigma transpose epsilon 0. Okay, anyway, I mean this is very straightforward if you understand sigma transpose epsilon 0 and if you put it as sigma 0 d epsilon 0. I'll explain this in the next class. What it really means is any strain, initial strain, you can talk in terms of initial stress or vice versa. We will discuss this in a later class. I hope you understand this. Any questions? Any questions on it? Okay, please go through it. If there are any questions, I'll answer it in the next class. Okay.